Welcome, ladies and gentlemen, to this video lecture. Okay, let's take a look at this theorem. So let A, L, and M be real numbers. Let f and g be functions defined on an open interval I containing A, except possibly at A. This theorem says if the limit of f is L and the limit of g is M, and for all x in I, f of x is less than or equal to g of x, then the limit L is less than or equal to the limit M. So let's just make a little intuitive sketch here of what is going on. So let's say A is over there, and we've got two functions. So f is like so, L is over there. So L is defined on an interval, let's say I. So over here is an interval I containing A. F is, let's say the graph of f looks like that, and let's say the graph of G looks like this. So everywhere on I, so everywhere on this interval I, G is bigger than f. Then what this theorem says, that the limit, if G is bigger than f everywhere over here, then the limits satisfy the same relation. So the limit of L is less than or equal to the limit of, or the limit of f, which is L, is less than or equal to the limit of G, which is M. Okay. And this theorem is interesting because one way of proving it is a proof by contradiction. So let us do that. So I'm going to start over here. Of course, first thing we do is we write our proof outline. Proof outline. Not outline, outline. Okay. We want to assume that the limit of f is L, limit of g is M, and that for all x in I, f of x is less than or equal to g of x. Under these assumptions, we then want to show that that L is less than or equal to M. Okay, let us prove that. Okay, what are our assumptions? We will assume the following. The limit as x tends to a of f of x is L. The limit of x tends to a of g of x is M. And so let's call this A and B and C. And C is a quantified statement for all x in I, f of x is less than or equal to g of x. So here are our assumptions. So now let us suppose that this conclusion is false. So we want to use a proof by contradiction. So we will suppose that L less than or equal to M is false. So suppose L is not less than or equal to M. In other words, that L is greater than M. Okay. So before we proceed here, let's go back up here and let's make a little drawing of what we are supposing. So we are supposing that L is greater than M. And the limit of f is L, and the limit of g is m. So we see here, if we suppose L is greater than m, we see here that we have this positive distance between L and m. And so we can use this positive distance to separate these 2 points. Okay, and then we can use the definition of the limit to take this distance as an epsilon to construct a delta for which all the function values of g for everything in this interval around a is less than the average of L and m, directly in the middle. So all the values here of g will be less than the average. And similarly, we can find an interval here using the definition of the limit, so that all the values of f here will be above, strictly above the average here. But if that is the case, then you take any value here, and that will then contradict the assumption. Remember, so our functions are defined on this interval I. This will contradict the assumption that f of x is less than g of x for all x in I. So that is the idea. Okay, let's do that. So we assume the following. Assume that the limit of f is L, assume the limit of g is m, and for all points x in I, f of x is less than or equal to g. Okay. And now, to use a proof by contradiction, we will suppose that the conclusion that we want, L less than or equal to m, is not true, i.e. that L is bigger than m. Okay, so now we want to end up with some contradiction, and the contradiction that we will end up with is we will contradict this assumption that we made. Okay. So, let's see. What is this distance from the average L plus m over 2 to m? Let us take a look there. What is that distance? L plus m over 2 minus, and what did we have there? M minus m. Let's write it this way. That is equal to L minus m over 2. And you see here, if you take the L, the m across, L minus m is bigger than 0, so L minus m is bigger than 0. Okay. But let us define epsilon as L minus m over 2, which is bigger than 0. Now we are going to buy deltas from shop A and shop B, which work with this epsilon. So buy A. There exists a delta, let's call it delta 1 greater than 0, so that what happens if 0 less than x minus a less than delta 1, then we're using shop A, f of x minus L is strictly less than epsilon, which we define to be L minus m over 2. And let's work a little bit further. Let's see. Let's not do that now. We shall do that in a moment. Or let's do that now. So to see under this condition what happens. So let us expand, or let us use the definition of the absolute value to get the following. So f x minus L is less than L minus m over 2 and is greater than L minus m minus L minus m over 2. Let's take this part and let's take the L across. So so that we get f of x is bigger than, what will it be? L, let's put L over 2, 2L over 2 minus L plus m all over 2. So f of x, let's see, that plus should be a minus. So this becomes L plus m over 2. So we see here what happens. Under this condition, we obtain this. So if we expand this, if we manipulate this a little bit, we see here that under this condition, f of x is always bigger than the average of L and m. So f takes on values that are always bigger than the average of L and m. So always above this line. And now we will do the same thing for g, but we will see that g takes on values that are always below the average. So let's do that. So by b, now we're going to use the assumption for b here. And we are going to use the same value for epsilon here. So by b, there exists a delta 2 greater than 0, so that if 0 less than x minus a is less than delta 2, then what happens? G of x minus m is less than epsilon, but epsilon we define to be L minus m over 2. L minus m over 2. Okay. And now let's do the same thing we did before. Using the definition of the absolute value, we obtain that g of x minus m is less than L minus m over 2 and is greater than minus L minus m over 2. Let's take this m. Now instead of using this side, like we did for f, we will use the other side. Let's take this m across and simplify. So we get this, take the m across, simplify. G of x is always less than, that becomes m, let's write it as 2m over 2 plus L minus m over 2, and that then becomes, so we get g of x is less than or is strictly less than, that becomes 2m minus m, which is m, plus L, which is, so g of x is strictly less than the average of m and L. So under this condition, so if this holds, then that holds. So if we go back here to our diagram, we see here we can find a interval centered at A with radius delta 2, so that the values of G are always smaller than the average of L and M. That is what we have there. And now to obtain a contradiction, we just say let x be any number satisfying the following. So it's satisfying, and x needs to be in I, satisfying the following. 0 is less than the absolute value of x minus a is less than the minimum of delta 1 and delta 2. Then we have the following: x minus a is less than delta, which is less than or equal to delta, is less than delta 1, and 0 is less than absolute value of x minus a less than delta 2. But since these conditions, if these conditions are true, then what do we have? We've got f of x is, or let's do it the other way around. G of x is less than L plus m over 2 from here, since this is true, and we've got since this is true. From the other side, we've got f of x is bigger than the average. So this is less than f of x. So here we have now constructed an element in I for which g of x is less than L plus m over 2, but this same x, f of x, is bigger than L plus m over 2. So g of x is less than f of x. But this contradicts our assumption. What does it contradict? This contradicts assumption C. Assumption C says for all x in I, f of x is less than g of x. So what has happened here? We have now, maybe let's erase this again. We have now found here an interval for which f takes on values above the average of L and M, and G takes on values below the average of L and M on some different interval. You take an element in the intersection of these intervals, then G of X will be less than L of M, F of X will be greater than average of L and M, but that contradicts our assumption C. So here we have that which contradicts our assumption C. Our assumption C, which is for all x in I, that f of x is less than or equal to g, because here we have now constructed an x in I for which g of x is less than f. So somewhere something is wrong. What is wrong? Our supposition here is wrong. So therefore our supposition, our supposition that which way around was it? That L is bigger than M is wrong. Therefore our supposition L bigger than M is false, and we conclude that L is less than or equal to M. And that concludes our proof. Okay, so let's just go through it again. So we want to prove this. We want to prove this implication. If these three assumptions are true, then our conclusion here is that L is less than M. So we suppose that L is greater than M. If L is greater than M, you've got a positive distance between L and M. You take the average. You look at the distance between the average and M. You call that epsilon. That means you can find an interval around A on which G is less than the average from how you constructed this epsilon. You can also find an interval around A on which F is greater than the average, L plus M over 2. You take any element inside the intersection of these two intervals, and this element, X, if you look at the values of f of x and g of x there on the intersection of these intervals that we just constructed, the value of g will be less than the average, the value of f there will be greater than the average. But this is the wrong way round. This is the wrong way round. So we get this value of f at this point is greater than the average, value of g is less than the average, but this contradicts C. C says the value of f is less than or equal to the value of g for all x in I. And since that contradicts that assumption, we must have that something is wrong somewhere, and what is wrong? Our supposition that L is greater than M is false, and we conclude that L must be less than or equal to M. Okay, and that is it for this theorem. I will see you in the next one.